Hey there, and welcome to my lesson on Euler's method. Leonhard Euler was I believe, an 18th century mathematician. He is one of the more prodigious uh, authors of math papers of all time. He is kind of a big deal as far as mathematics is concerned. Um, some math students in high school might get introduced to the name Euler in geometry, because that's kind of one of the first things you might see of things that he has published, where you identify how many faces, vertices, or edges a polyhedron would have based off of his work or his equation that he developed for that. But it's also very possible that you never saw that in geometry because it's kind of a niche thing, and maybe spent teachers often will say, well, it's a very minor thing as far as geometry is concerned, and they often skip it in lieu of things that they consider to be more beneficial for students' understanding. But what we're going to be looking at for that Euler gave us today is a method of analyzing differential equations to approximate what their solutions are going to be. Uh, Euler's method is going to be something that you would use on various circumstances, meaning that sometimes you'll have a differential equation that simply isn't going to be separable or solvable using standard means of trying to solve it. So using Euler's method to get an approximation is going to be good enough. Sometimes, as tedious as Euler's method can be sometimes it is simply the least painful option to identify the solution or an approximated solution of a particular differential equation. There's several reasons why you may want to use it, but this lesson is meant to show you how it's used in the first place. So here, moving on, this is essentially what Euler's method kind of looks like. What it's giving you here is you have a curve that represents the curve of some differential equation. That's the solution curve. Now, normally when we solve a differential equation, at some point we have to integrate it, and if it's an indefinite integral, of course, we have to have that constant of integration, meaning that there's an entire family of solutions that could be used for a particular differential equation. We need to be able to identify what the specific constant of integration would be. And we can represent that stuff using a slope field, like what we're seeing here. Here we can see the same idea with the slope field, where we have, slope field, of course, being made up of small segments of tangent lines that would represent, uh, you know, derivatives of a curve at a certain point. Well, let me come back up here just in case anybody needs to finish looking at what that big idea is. Euler's method is a way of approximating what the solution is of a differential equation is going to be at a certain point along its curve. If you notice, what we're looking at is we start off with the initial point, P naught, and then we go to a new point, which you're calling P sub 1, P sub 2, etc. Well, those increments along the x-axis, the delta x or the step size, those are just small increments that we take along the curve in order to get an idea of what it's going to be. So you can kind of see that in this case, because the function is going to be kind of concave down, our tangent line approximations are going to be above the curve, meaning that everything that we would have would represent an overestimate approximation. The best kind of analogy that I can think of for Euler's method for something that any casual person might do is if you're hiking through the woods or something like that, and you want to make sure that you're maintaining a straight line. Well, you don't just pick a point on the horizon to try and follow and walk to that point. You pick a point along the horizon somewhere, and you pick a point somewhere close to you, and you line those up, and then you walk to the point that's close to you, and then you pick another point that's relatively close to you, and you walk to that point, and so on and so on. And that will give you the approximation of a walking in a straight line to a particular point in that case. But that's essentially what we're doing with Euler's method. We're starting off at the initial point, and we pick some point. Oh, we pick some point on the x-axis right here, and we say, okay, well, from here, from the initial point on the x-axis to somewhere else, we're going to make some small incremental movement, and then we're going to have this line segment that kind of connects it, and then we'll make another small incremental change. Now, ideally, I'm not sure if it's showing up here on the scale of the way that this is looking here, but the delta x should be the same each time when we're looking at this. But that's how we're using Euler's method. We're going to be kind of picking small incremental changes along the x-axis to help us evaluate with the differential equation, whatever it happens to be, to find out what the new y value will wind up being. And so here we see the same curves on the slope field for the differential equation, whatever it happens to be, with the exact solution curve plotted out for you along with the Euler's method approximation. And you can see how both of them are very much following the slope curves that we have for the field. But Euler's method is going to give us an approximation. It's not going to give us the exact value. So here they're giving you a little bit of background on who Leonhard Euler was. But what they're telling you here is that, recall, a differentiable function will display local linearity at any given point. Essentially what they're saying is that no matter what type of function that you have, if you zoom in close enough to it, it's going to represent a line. And that's essentially the foundation of what Euler's method is doing. Okay, so this is kind of what the slope tells you the direction to travel on a small segment, and then you just kind of repeat and repeat and repeat however many times that you need to figure out what your solution is going to be. So here, those of you that if you're following along with the notes for the video that I'm making for my class, you're going to notice that what I have here is missing the table that your notes are providing. Now, if you just happen to stumble across this video and you're watching it because you needed some help with Euler's method, then the table that go with these notes was left off on the presentation intentionally. So if you are following along with the notes for this class, at this point you may want to just have some scratch paper, a separate piece of paper other than the notes, because the table that was given to you, I think it's a little bit confusing. It's a little bit busy as far as what it's asking you to do. Okay, I'm going to make my own table to try to simplify things a little bit and make it consistent throughout the entire lesson. So it says write the equation of a tangent line for each point. Okay, now that's not necessarily what we're going to be doing. What we want to be able to do really is we want to be able to identify what some y values are going to be, so that way we could actually write those tangent lines. Okay, so here we have our differential equation, dy dx is equal to y, and we have our initial point here when x is 0, y is 1, and they're giving us our step size, our delta x. Okay, so typically the way that I like to look at Euler's method whenever I'm having to do it is I like to kind of here, let me pick a different color. A lot of times what I like to try to do is I just say, okay, well, we have x, and then what we're going to do is we're going to kind of do something that'll give me a y. Now, some presentations, they'll put the table that they're creating, they'll put the y right next to the x because you're used to seeing x and y together. I'm going to kind of leave it on the right here because I just think it's going to be a little bit more understandable with what I'm going to do here. And in between, we have a process where I take the delta x, the step size, and I multiply it by the differential equation at whatever points that we have, dy dx. And we're going to add like the previous y number that we have. So here we're going to just give ourselves some semblance of a table. Now it gives us our initial point being when x is 0, y is 1. So for the initial point, we don't actually do this because we were given the initial point. We start doing the stuff that I have in the middle column when we start getting our new points. And let's see. Now the x values that we are going to be looking at, those are going to be easy to identify because the x values change by the step size each time. Now what it's asking you to do, again, if you happen to have the original notes for this, it walks you through 5 steps. So we start with the initial point at 0, and then we go 0 0.1, 0 0.2, 0.3, 4, and 5. Now that's what the table was giving in the notes, and you could do however many step sizes that you needed to. Now, real quick before we actually start doing any filling into the table here, if you don't have a calculator, you definitely want to have a calculator to help you with the arithmetic here because you're going to be seeing all kinds of long decimal numbers when you do this stuff with Euler's method. It's definitely going to be something that you would, be getting on the calculator portion of your multiple choice test if you take in an AP exam. So definitely have a calculator to help you with this, okay? So let's try to color code at least this first one, okay? So let's look at delta x. Well, let's do delta x here in blue. Delta x is always going to be the same. It's always going to be 0.1. So 0.1. And it's going to be multiplied by, let's do green here for the differential equation, okay? Now the differential equation in this case, dy dx, is just equal to y. Now, in some instances, what it might tell you to do, it might tell you to take the dy dx, it might tell you to take this and solve it, separate the variables where you would have like 1 over y times dy is equal to dx. And then you would integrate both sides to, try to find like a general solution for it. Okay, I'm not going to try and separate the variables. I'm going to just use the differential equation the way it was given, and I will just substitute whatever x or y values into the differential equation and simplify it. So if I take what I'm doing is I'm taking this 1 because that's the y value. That's the only thing that we have, and I'm going to take that y value of 1 and I'm going to substitute it in here. Okay. So in that case, dy dx simplifies to just be 1, because that's all we have, literally. Well, now what we're going to do is, and I already have blue, so let's do, I guess, purple. Now we have to add some y value. Well, this y value here, this is the previous y value from whatever step came before it. In this case, the previous y value in this case for my first step that I'm working with is going to just be that 1. So I'm going to say delta x times dy dx plus the previous y value. Oop, and I don't want to write y. In this case, the previous y value happens to be a 1. So if you do this on your calculator here, you're going to end up with a new y value, In this case, and let me go back to my red, of 1.1. And then we just kind of go into a rinse and repeat cycle. We just kind of keep doing that to fill in the table. So in this case, delta x, let's go to the next one. And again, if we wanted to write the equation of the tangent line at this point, we could, because we know the derivative at a certain point, and we know an x and a y value at a certain point, and we could fill that stuff in if we wanted to. But right now I'm focusing on just filling in the table. So moving on to the next step, here if it says 0.02, we want to know what the y value is going to be on this second step. So delta x is still the same, it's just 0.1. Now in this case, dy dx changes, because now I'm going to take whatever the previous y value was. I'm going to take that previous y value, and again, it just gets plugged into the differential equation, which in this case is just going to be 1.1, because that's all the differential equation is. It's just the y value. And then we add the previous y value. Well, the previous y value is again 1.1. And if I do that on my calculator, we're going to wind up with a 1.21. And then we keep going. So the next one, again, delta x is just going to be 0.1 because it's consistent throughout the entire process. Delta x, I'm sorry, not delta x, but dy dx for this one, again, is just going to take the previous y value, or in this case, we're only substituting the y value because that's what the differential equation only uses. It only uses y. Otherwise, we would use x and or y. It just depends. So in this case, again, I'm going to wind up with the previous y value of 1.21 plus the previous y value of 1.21, and that will give me 1.331. And we just keep going. So here, 0.1. When I substitute, into the differential equation with the y value of our previous step, we get another 1.2. Nope, not 1.21. 1.331 plus the previous y value 1.331, and when we work that out on the calculator, we get 1.4641. And then finally we get to our last step, 0.5 of 1.4641 plus 1.4641, and again, I think this is starting to illustrate how tedious Euler's method can be, but again, in some instances, this is literally the best option that you have to try and solve certain differential equations. So here I get 1.6, oops, 1.61051. Okay. So if I wanted to write the equation of the tangent line here, let me just give me 1 second here. Let me grab something. Okay. So this is essentially what Euler's method is asking us to do. Now this particular example is asking us, well, could you write the equation of the tangent line at each particular point? Well, sure we could. I'm not going to write it out for each and every one, but we can just kind of pick a particular one and go from there. Let's try doing this here in black. So if we wanted to write the equation of the tangent line, well, let's just pick a random one. Let's pick this one right here. If I wanted to write the equation of the tangent line at that point in point and slope form, we'd say y is equal to, well, the slope at that point, you just take the differential equation to get the slope, and in that case, when x is, 0.2 and y we wind up with the 1.21, well, that is the slope of the tangent line at that point. And let's see, I just want to double check, make sure I'm going to write this down right. Hold on a second. Okay, my mind is messing with me this morning here. So yes, the slope is the value that we get when we take the previous y value and we substitute it into the differential equation. So the slope at that second point is the 1.21 value that we get, and then we'd say x minus whatever the x value is, in this case x minus 0.2, plus the y value at that point, which is 1.21. So that's how we would write the equation of the tangent line at that particular point. And we could do it for the rest of them, but I'm not going to bother taking the time to do that. So that, in effect, is what Euler's method is asking you to do. Now, as far as the table is concerned, some teachers or some textbooks may make the table where they say x, y, and then they'll kind of do that delta x times dy dx plus the previous y value. They may do the table kind of more like that, where x and y are together, as opposed to where I put the y column to the right of the operation that we did to get the y values. But that's kind of a personal preference. So here, when it says where they're giving you some methods for solving differential equations with Euler's process here, the first thing it says to do is it says solve the differential equation for dy in terms of x, y, and dx, and that's not what I did. I left the differential equation exactly as it was, and that's how I'm going to continue doing it. If you want to use that, it's fine. It'll give you the same solution, but I'm going to try to keep things consistent. Okay. Let's see. Substitute values of x, y, and dx to calculate the value of dy. Okay, which is what we've been doing. That's what I did on the first example. Find the approximate new value by adding the previous y value. Okay. And continue this procedure. Then to continue this procedure, that's where the tediousness kind of comes in. So here, now they're giving us a better differential equation to work with, where they're saying, show that Euler's method for the differential equation, 0.5 times the sum of x and y, starting at 0.2 and 1.11, so there's the initial condition, using two steps, gives y is equal to 1.775 when x is equal to 0.3. Now, in this particular example, they're telling you what the answer is going to be. Okay, they're telling you that you should end up at that point. Okay, so at that third point of 0.3, we better have a 1.775 when we're done. So we can go ahead and just kind of put that there and understand that that's where we should be at when we're done. And that's just how this example was written, meaning to give you that. So our step size, our delta x, is going to be 0.5. So this is 0.25 and 0.3. So those are the two steps that we are taking in order to get to that 0.3 spot when we're supposed to be done. And we should have 1.1775 when we're done. So how do we get there? Okay. Now here, what they're showing you for delta y, I'm still going to use the same process that I did in the first example, where I'm going to say delta x times the differential equation results, dy dx, plus the previous y value. Okay. So for the initial conditions, we don't really need to do anything here. I'm going to just kind of leave this part blank. Okay. And what we're going to look at now, and this is, I'm really not even going to look at this column here because it's really not necessary. This middle column, or this column here with the y values, to me it's not necessary. This is what I would be looking at of just the column for x, the column for the work that I'm going to do to get my y values. Those are the three columns that I really care about. So how do I figure out what the new y value is going to be? So I'm going to just kind of X that out here. Okay. So delta X in this case is given to you to be 0.05. So I'm going to say 0.05 here. Now dy dx is where I take the X and the Y values and I kind of plug those into the differential equation. So I'll just, let me find a little blank space here on the whiteboard. Okay. So if let's just do it up here up at the top. So dy dx, and you could just do this on your calculator off to the side or off to the side on your paper somewhere. And in this case, we're looking at it when we substitute the initial conditions of, in this case, 0.2 for x and 1.11 for y. So we're going to say 0.5 times, and in this case, we're going to say 0.2 plus 1.11, and all of that is going to equal 0.655. So that's what I substitute here for the dy dx, is the solution of the differential equation when I substitute whatever the previous x and y values were. So here we're going to say 0.655 plus the, and I go back to my black color here, plus the previous y value, which in this case the previous y value was the initial y value of 1.11, and that gives me my new y value, in this case of 1.14275. And then we kind of keep going. So we have only two steps that we're taking from the initial condition in this example. But ideally, we're going to again wind up here when we're done doing this next step. So again, the delta x doesn't change. It's 0.05. Now delta y, or the dy dx, that is going to change. So now if I do that again, and let me get rid of this bit here, and we can repeat it with the second step. So if I say dy dx, and now what we're doing is we're looking at the 0.025, nope, not 0.025, but 0.25, erase. So 0.25 and the 1.14275. I'm going to get 0.5 times 0.25 plus 1.1. I keep forgetting that 1 at the beginning. 1.1427575. And that whole thing equals, in this case, I don't have it written down. I didn't write it down on my paper. Hold on a second. Let me write it, figure it out. All right. So when I do the differential equation solution here, I'm getting 0.696375. So that's what I'm going to have here, 0.696375. And when I add the previous y number to that, which in this case is the plus 1.14275, we should be getting 1.1775. Now the calculator is actually giving me a value of 1.17756875, but you can see when we're truncating it, we are getting the number that the problems said we should get if we did our Euler's method correctly. So that is what we're looking at with, let Here's our second example with Euler's method. It's giving us a better differential equation than we saw in the first one, a more typical type of starting point than, again, what we saw in the first one. And we were able to establish, hopefully, a good process, a consistent process for using Euler's method. So here, this next example, I strongly encourage you to pause the video and try and work this one out in advance. But if not, feel free to follow along. But this particular problem, this example, is probably the most similar to what you may expect to be given as a question on an AP exam. This one is a pretty standard kind of Euler's method problem where it says approximate 4 points on the solution curve to the given differential equation starting at the initial point 0, 2 with your step size being 0.1. Now, of course, that would be the problem, and then you would probably be given, just some, your 4 multiple choice answers or options, and, the table would be something that you would have to kind of make yourself. Okay, so in this case, we're going to be looking at, again, here, and let me go to a different color here so not everything looks the same. Here in this column that they have, I'm going to, again, keep things consistent. I'm going to say dy dx, or delta x times dy dx plus the previous y value. And we'll go ahead and fill in this last column simply because it's there. But this one's going to look a little bit more typical as far as we have our x column, the column where we do our work to figure out what our new y value is going to be. And again, you can see that first row here where we have this dotted line, we don't need to do anything there because we're just filling in that stuff with our initial points. And again, this is where I say feel free to pause the video and see if you can fill in the rest of the table here, because if you can, then you should be in pretty good shape for pretty much anything that you would see with Euler's method. Okay. Now the x column, that's the easiest thing to fill in based off of the step size. So here this is going to go 0.1, 0.2, 0.3, 0.4. Okay, and that's just based off of the step size of delta x being 0.1. So here, delta x being 0.1, I'm going to say 0.1 times the result of dy dx. Now in this case, when I take the dy dx and I substitute it into the function, I don't have it written down as the number because I think that the numbers kind of got a little ugly to write down. So what I'm going to do is I'm going to just do the substitution with the differential equation. So we have -3 times 0 squared times 2, where we're just taking the previous x and y values and substituting into the differential equation itself, plus the previous y value of 2. And when I do, I wind up getting a 2. Which makes sense because this stuff here in the brackets, all of that's going to simplify to be a 0. So my new point would be 0.1 and 2. And we'll just kind of keep repeating the process here. So here 0.1, delta x is constant in the process that we're doing. -3. Now here I'm going to substitute my previous x value, which in this case is a 0.1, and I square it. And the previous y value in this case is a 2 again. And I say plus 2. And if I type all of that into my calculator, we're going to get a 1.994. So my new point would be 0.2 and 1.994. For the third step, moving on, delta x again is constant, 0.1 times -3. The previous x value in this case is going to be the 0.2 squared times the previous y value, 1.994, plus the previous y value, 1.994. And if you type all of that into the calculator, you're going to get a clunky number here of 1.970072. So my new point is at 0.3 and 1.970072. And so the last row here, this is usually where the answer choices are going to be, or this is where you would find the solution that you're typically going to be asked to find. It's like, what would it be after the fourth step, kind of thing. So here, 0.1 times the results of the differential equation, -3, substitute the previous x value, 0.3 squared, times the previous y value, 1.97072, plus the previous y value, 1.97072. And I'm going to, this one I have it written down. I think I abbreviated it here, where I'm saying 1.91688. And so that might be like this point here, 0.4 and 1.91688. That might be what we would have as an answer choice that we're looking for. That is, this example here is probably the most typical of something that you would be asked to do as a general multiple choice question, where they just give you the question. The table is obviously not given to you. You have to know how to make the table to work through the process. But there we go. That is, what we're looking at, generally speaking, for Euler's method. It's, just like everything in math, there's an algorithm that you follow. You just need to understand what the algorithm is and go to town and see what you wind up with. Now, of course, Euler's method is an approximating, it gives you approximate solutions. It doesn't give you exact solutions. So there's going to be an error, and this is what we're getting into next as far as how we figure out what the error is going to be. And again, definitely make sure you have your calculators, you're working this stuff out. So it's giving you a couple of tables. It says compare the tables for dy dx equals y. That was the first differential equation that was a differential equation from the very first example that we had. And the particular solution for the differential equation, which happens to be y is equal to e to the x power. So here, these are the tables that we got. The table on the left is what we did in the first example. The table on the right is the solution of the particular solution of the differential equation, y is equal to e to the x power. And what we're going to be doing is we're now going to be comparing the outputs at each particular point in the step. Now, in this case, y is equal to e to the x. That should be a pretty standard exponential function. Everybody should be able to understand just from the equation itself that it's going to be an increasing function over time, that it's going to be concave up. And so the function that's kind of graphed here for you is essentially what you're going to be seeing is, as far as what the actual solution curve would be and what the approximate solution curve would be. So here, why do the approximate y values underestimate the actual values? Well, in this case, this is based off of the shape of the curve, really. Okay, the tangent line that we create is going to be under the curve, which is concave up in this case. So here I'm saying in this case each tangent line will lie below the curve. Therefore, the solution curve of y is equal to e to the x being concave up, and we use these tangent lines to get these approximations. That's why it's going to be an underestimate. Now here, what it's asking us to do, it's asking us to compare the actual solution with the approximated solution. So at when x was equal to 0, what was the difference? Well, the difference was 0 because we started at the same place. But as we move on with our steps, here, this difference is about 0.005 between the exact value and the approximated value. And we're just filling the table using the exact same method. We just take the corresponding x values and take the difference of them. And you can see that the difference is growing from 0.005 to 0.001 to 0.02 almost, to almost 0.03, and so on. So the error is getting bigger. The further that we go, the error is getting bigger. And it's what can you do to make the solution curve more accurate? Well, the only thing that we could do to make it more accurate would be to change the step size to make it a smaller delta x. That's really all we could do. And that was one of the issues that digital music companies were doing when they're trying to convert everything that was recorded as an analog signal to a digital signal, because a digital signal is an approximation of its analog component. And so the way that they would make it more true to sounding like the original would be to give you a bigger sample size, make the change in x smaller from point to point. Now at this point here, this is where we're going to be looking at it graphically on our calculator. So we're going to take a look. If you happen to have your Inspire calculator handy, you might want to look at this. Now, if you don't have an Inspire, I'm not sure what instructions necessarily that you would use, because I've only ever done this on the Inspire calculator. I've never done it on anything else, so I'm not sure what the instructions would be. But here on the Inspire calculator, we're going to take a look at this differential equation at the initial point with a step size of 0.25. So what it tells you to do, it says in your scratch pad on your calculator, we're going to do the following steps. Now in this case, we want to go to our calculator. We want to go to the graphs, and we're going to say hit the menu button. And you may need to bear with me here because I'm still a relative novice. I'm still kind of learning the calculator. But we're going to go to our differential equations. And next, what it tells you to do, if you are kind of following along, edit the parameters to, oh wait, we got to actually, okay, I didn't finish filling in the stuff here. It says we're going to enter the differential equation here. Now, I don't think I'm going to hit enter just yet. But one of the things that you notice from what it's telling you to do here versus what the actual differential equation was, if you notice here, it's just y, but what we enter into the calculator, we need to make sure that we put that 1 on there. And the reason why is because if you notice, the calculator needs to know, well, what y value are you doing it in regards to? And because this is y1, that's why we need to put a y1 when we type it here. So we're going to say y1, and what was it, minus 2x. So this is going to be our differential equation. Now before we hit enter, I'm going to just go ahead and follow on with the next things that it's telling you to do. We're going to, in this parenthesis that we have down here, this is our initial condition. And I know the calculator understands it's the initial condition because it's x naught and y naught. That's how we know it's the initial condition. So in this case, we're at 1 and 2. And then it tells you to kind of come over here to these little dots where it says edit the parameters. We're going to kind of, click over to those 3 dots where we can edit the parameters. So here, the solution method Euler, that's pretty standard. Even if you're not trying to use Euler's method, if you're just trying to graph a differential equation, this is always going to kind of be there. And the next thing that it tells you to do, according to the instructions, it says meet the step size of 0.25, okay? And it's kind of showing you, let's go back to the calculator. Uh, and again, it's showing that we're going to be placing it on a slope field. And if we just kind of scroll down here where it says the plot step, this is where we're going to change it. We can change it to 0.25. And the field resolution, the standard field resolution is 14. You can make it more accurate if you want to. You could double the field resolution to say a 28, and it'll just look, it's kind of like the difference between maybe a 16-bit graphic versus a 32-bit graphic. It just has a better resolution. It looks cleaner. And then we can say OK, and we wind up with something that looks like this. So this is the Euler approximation, okay, of what we are given with our differential equation. Now, what are the next instructions? Did I do everything that it says here? It says click menu, trace, or menu and trace, and then graph trace, and use the left and right arrow to trace through the steps. And you'll see below, you can see the initial condition. So let's go ahead and do that. So I'm going to say menu, trace, graph trace, and we'll just kind of go through it, get our approximated values, and they should be matching from what we had on our table. But I don't remember the table values offhand, but that's what it's asking you to do. And then it says, well, what happens if you change your delta x to 0.05? So let's go hit tab here, go back up to this, hit my 3 dots, and I'm going to go down. So instead of my plot size being 0.25, now let's change it to 0.05 with what it told us to do. Okay, and we click OK. And you can see here, this is going to be a whole heck of a lot more, precise as far as what it's giving us for our possible solutions. Now, I haven't bothered to find the general solution or the specific solution to the differential equation, but if we did, and we graphed it in tandem with the Euler's approximation, it should look pretty much like this. Okay. Now again, because this is going to be a concave down function, the actual solution curve is going to lie below the tangent line. So all this Euler stuff is going to be an overestimate in some way, but it should look very much like what you see on your screen at the moment. So that is going to wrap up what I have about Euler's method. It's a way to approximate the solutions of a differential equation without needing to have to find the specific solution necessarily, because sometimes it's just going to be too difficult, or maybe it may not even be possible arithmetically to get a solution. And hopefully we got the idea of the table being we have to take the x value, the initial conditions that we had, substitute them into the differential equation as it was given to us, and multiply that by delta x, and then add the previous y value, and we just kind of keep doing that and doing that and doing that for as many steps as we need to take for the given problem. But I hope this was good information, useful information. Thanks for watching, and until next time, guys, take care.